Hello everyone, we are Team 12 and our project was a motor-assisted sled for sled hockey and our advisor was Dr. Fred Allen.
Sled hockey is a sport that's similar to ice hockey, but for people with lower body disabilities. Instead of wearing ice skates to move around, the players sit in a sled and push themselves with modified hockey sticks. Our group members and advisor have basic knowledge of the sport, but needed to learn more, so we reached out to members of the sled hockey community for advice and feedback to better understand our user need. We learned that there are about 100 sled hockey programs in the U.S. consisting of over 3,000 participants, and it is rapidly growing as one of the most popular paraplegic sports.
Young and inexperienced sled hockey players have difficulties pushing themselves due to either a low muscle mass to body weight ratio or upper or full body disabilities such as spina bifida or cerebral palsy. The age of the players that are most commonly dealt with these issues are around 6 to 12 years old, and the current solution, which is shown on the image at the right, shows a handle attachment to the back of the sled, allowing an able-bodied adult, known as a pusher, to propel the young player across the ice. These pushers allow for players who cannot push themselves to participate in the sport. However, they come with an extensive set of limitations. The pusher takes away players' control and their competitiveness. The players also lack independence and involvement because they rely on a pusher to make decisions on where to move and how to play. The role of being a pusher comes with an extensive set of rules that disrupts the flow of the game and limits accessibility for players needing assistance. The rules state that only 2 pushers are allowed per team and on the ice at a time.
The objective of our project is to create an alternative to the typical push sled for athletes unable to compete on their own and to allow sled hockey players who require pushers to be able to propel themselves without the help of another person. Through our design, we hope to enable a more diverse athlete population with a wider range of disabilities to engage in the sport. A motorized propulsion system will be designed with the intention of allowing these players to be more independent and self-sufficient on the ice. The system will be designed to fit on a pre-existing sled. There are various constraints that influence how we can design our sled accessory. The final project is due June 2021, giving us a 9-month period in which we must design, develop, and test a prototype. Through partnership with both BMES and the Closed School of Entrepreneurship, we were able to obtain $1,500 in funding. This budget will allow us to purchase a battery supply, a motor, a variable speed controller, raw materials for a frame, and any other costs that are required. We were also able to receive a brand new sled donated by the DC Sled Sharks organization. We were fortunate to already possess much of the necessary privately owned equipment to produce a prototype. We used both the USA Hockey official rulebook and the NTSB regulations for motorized vehicles as guiding factors in our build. The sled must be able to perform in a cold, wet environment as low as 40 degrees Fahrenheit since it will be used on ice. The overall system must withstand shock from sled collisions at max speeds as well as puck or stick strikes that will occur during normal gameplay. Using image and video analysis of a sled hockey game for a specific age group, it was determined that these players' top speeds are around 3.25 meters per second. It was important to determine a top velocity since the motorized sled should not exceed the abilities of a standard sled user. As the players propel themselves with the additional components, the entire unit must provide the same balance as a normal sled. Players should be able to maneuver with ease and without interference from the attached system. The unit must also notify the user if it does not work properly or if the battery is critically low. In the event of tipping, power should shut off, protecting the user and other players from injury. In adherence with USA Hockey official rules of sled hockey, there can be no obstructions between the front of the sled and the blades, as can be seen in the top right picture. The bottom of the seat cannot be more than 20 inches off the ground, and the entire system can be no wider than the width of the seat, which is a maximum of 18 inches. The system should also be designed so that the sled can be controlled hands-free with the harness, as can be seen in the bottom right image. It should also have easy access to components for adjustments and repairs. A well-defined project scope was essential to ensure the continued success of our project and refine our requirements. The sled retrofit was broken down into 3 different subsystems. The propulsion system is how we plan on actually moving the sled without the use of a pusher. The scope of this subsystem consists of mainly developing the battery and motor requirements. The controller system represents the interface that communicates between the player and the propulsion system. This system will allow for speed and acceleration variability. It will include sensors that will work cooperatively with the players to keep them safe, The last subsystem is the physical sled design. This scope includes positioning the physical components of the retrofitted sled and providing protection to the components during gameplay. The sled should still feel balanced, intuitive, and safe to use.
The requirements for our solution were broken down into these three subsystems. For the propulsion system, the sled must withhold the target user weight of 25 to 50 kilograms, which were taken from the CDC growth charts for the 5 to 9 percentile of males and females from the target age of 6 to 12 years old. The battery must last one half of a sled hockey game, which is 30 minutes, and the battery must be easily interchangeable to be switched out between halves. The sled must also reach a top velocity of 2.9 meters per second and reach a constant acceleration of 0.77 plus or minus 0.2 meters per second squared. And these values were determined using video analysis of a sled hockey game of players in our target age range. For the controller subsystem, the user must have easy access to an emergency stop button that cuts off all power to the system, and the system must be able to shut itself off if it tips 30 degrees in either the left or right direction to protect the user and other players from any exposed propulsion system. This will allow the design to not produce any additional risk to the game that does not exist currently. The user must also be able to control the system through a cable actuator that allows for a gliding ability and variable speed control. This will give the user complete control of the system and allow for them to integrate right into an existing sled hockey environment. For the physical sled design, the sled must bounce on its blades when the propulsion system is engaged with the ice as a normal sled would, which will allow the player to have control on their sled and keep from any additional difficulties with the frequently occurring tipping over of a sled during gameplay. And all sled components must comply with an IP55 rating to ensure waterproofing of all electrical components to protect the sled system and the users.
This is our final prototype build. The picture on the left shows the entire retrofitted sled, including the fabricated attached system. The picture in the middle shows the electronic components that power and control the propulsion. The picture on the right shows the back of the sled. Here you can see easy access to a power switch, charging port, and an LED that shows when the tipping event has occurred. The motorized wheels are enclosed by 1/4-inch aluminum, protecting the motors that sit inside from pucks, sticks, and players. There are 2 rods that now fully penetrate the frame, allowing for both motors to move in unison. This creates uniform contact with the ice, resisting the tendency for the sled to veer left or right. The large center rod and additional levers on the inside of the frame were added to resist shearing and allow the wheels to land flat on the ice surface. An electronic enclosure sits behind the seat and on top of the frame. It is designed to protect sensitive components from shock and water. Players can propel themselves using the mechanism shown right. When the user leans forward, this will pull on a cable and activate the levers, which allow the motors to engage with the ice surface and propel the user forward. The more the user leans forward after engaging the ice surface, the faster the user will go. As the player leans back, the counter tension from the torsion springs will allow the motors to disengage with the ice, causing the user to glide.
The electronics were designed for safety. A shutoff switch will cut power to the motors in the event of an emergency. A gyroscope sensor measures the angle of the sled, and the Arduino has been configured to stop the motors when the angle exceeds 30 degrees. A lithium polymer battery drives the brushless DC motors through an electronic speed controller. It is easy to conceptualize through this drawing how the components interact and communicate, and with the more complex drawing, you can see how the electrical system was designed and assembled. The hardware itself is mostly housed in this rugged enclosure to reduce vibration interference and for waterproofing. It was designed for ease of access to the Arduino and VESC, which both require connections for programming. Wiring that could be hard mounted were soldered to the prototype board that connects directly to the Arduino.
Here's a demo video of the sled being powered on and the motors being engaged. You can see here that I pull a cord that is attached to the potentiometer, which then turns on the motors. You can also see here the modified tread that we attached to the motors to increase the traction between the wheels and the ice to propel the sled forward. Shown here is a table with the 3 verification tests that we performed along with the requirements that were tested. The 3 tests are the propulsion test, the battery test, and the tip-over test. Propulsion test verified the design can propel the estimated load with the required velocity and acceleration to verify requirement 4. The battery test verified that the battery would last for the length of 1 sled hockey period and satisfy requirement 2. The tip-over test was designed to verify that the gyroscope, which is embedded in the enclosure, would be able to cut off the power to the motors when the sled is tipped past 30 degrees.
This test tested the velocity and acceleration requirements. 30 kilograms were placed in the sled and the motors were engaged, allowing the sled to run in a straight line from the goal line to the blue line, which measured 19.51 meters, and Tracker 6 video software was used to track the movement of the sled to generate displacement and therefore velocity and acceleration data, and this test was repeated for a total of 5 trials. A summary of the data collected from the tracking software is shown on the right. The sled reached a max velocity of 4.41 meters per second and had an average acceleration of 0.55 meters per second squared. This means the sled passed our max velocity requirement as it was able to reach 2.9 meters per second. However, the test failed the acceleration requirement, missing the lower end of the 0.57 to 0.97 meters per second square range by 0.02 meters per second.
With time and testing conditions restricted, the battery was tested at a single load condition of 30 kilograms for the battery test. This is within our design range of 23 to 50 kilograms. At full charge, the battery was run with the average load mass for 3 5-minute intervals. The voltage was measured between each run to obtain battery depletion data. As shown to the right, the prototype passed the test. The annotated cutoff voltage is the programmed cutoff from the electronic speed controller. In the testing time, the battery lost 0.7 volts given the tread system that was selected. We were unable to determine amp hours lost due to the limited testing capabilities, but this test ensures that the current system will perform for the requirement of 30 minutes. The tip-over test is paramount to our safety requirement. The objective was to ensure that power to the motors stop if a roll condition exists. This sled was set level, powered on, and the motors engaged. The Arduino roll output was measured as the system was tipped smoothly. When the trip condition is met, the motor stopped, the red LED lights, and the angle was recorded. The system is returned level and verified that the LED is off. This was performed 5 times at the desired trip angle to measure tolerance of trip. This test did not pass due to drift in the trip angle. Trip angle increased as the test went on, creating an unsatisfactory condition for follow-on rolls. This result is indicative of potentially skewed normal axes in the gyroscope from not zeroing when the sled was reset level. Further prototyping is required to determine if vibration reduction mounts are required for the gyroscope or if a new angle sensor solution is more viable.
In summary, the propulsion test passed the maximum velocity requirement but failed the acceleration requirement. The battery life test passed as the remaining voltage was sufficient for completing a full half of a sled hockey game. The tip-over safety test failed due to a drift in the angle measurements that can only be fixed by upgrading the microprocessor.
First major design change was to make the accessory frame one solid piece. The frame would now be attached to the rest of the sled by sandwiching it between the blade holder and the seat. It was determined that the original design would produce excessive force on the rails shown left, and over time the rails would begin to bend. The previous design had wheels exposed to other players, while the new design has the motorized wheels now enclosed by 1/4-inch aluminum.
Our project required many innovations to meet the proposed requirements. The design is a first-in-its-kind electric-powered device that takes advantage of the advancements in small-scale electronic propulsion technology originally developed for electric skateboards. The increase in accessibility of these components allows us to incorporate a lightweight, customizable, durable electric-powered solution into the current designs to increase mobility and inclusivity. Shown here on the right is a video of me using the sled. As you can see, I only need to push when I need to change directions. And shown in the image below is our final prototype, which can move the combined weight of myself and the sled, totaling about 180 pounds. Our solution has the potential to have a tremendous impact on youth sled hockey. There are over 100 sled hockey programs in the US with approximately 3,000 participants, and the lack of upper body strength is a very common obstacle that inhibits many people from participating. There's a quote here from Norm Page, former USA sled hockey national representative. He stated that there are more kids who can't participate in sled hockey than those who can, meaning that the number of people who would benefit from assisted mobility exceed the number of players who currently play today. And it's based on this fact that we believe our product has the potential to increase sled hockey participation by over 100%.
Inherent to senior design, we faced many obstacles along the way. With a restricted budget, the microprocessor and tread design needed to be decided upon before implementation. Due to the nature of the prototype, ice time had to be secured to be able to properly test it at load conditions. Albeit new for senior design, COVID-19 presented an opportunity as well as a challenge for our group to develop our design remotely and safely.
There are many future revisions that the team considered to each of the 3 subsystems that would help improve this prototype. To highlight a few would be a more aggressive tread and more powerful battery to create a higher acceleration to meet requirements for varying loads, configuring the VSC to restrict the max speed within the requirements, a lighter, more versatile enclosure, and having a more consistent potentiometer that is mounted to the bucket.
At this point, we'd like to thank everyone from the sled hockey community and Drexel University who helped make our project our success, including our advisor, Dr. Allen, and instructor, Dr. Swoboda.
This concludes our presentation. Thank you for listening.
Hello, this is Team Sled, creators of the motor-assisted sled for sled hockey contributions deck. Here, each member will be discussing their contributions, challenges, accomplishments, and next career steps. The 4 team members include Cameron Neely, majoring in mechanical engineering, Ben Sauerwald, majoring in electrical engineering, as well as Jim Schickling and Joe Finlayson, both majoring in biomedical engineering. My name is Cameron Neely, and my main contributions to this project are sled design, part procurement, and on-ice sled and safety testing. I was responsible for turning the CAD work that Jim and I completed into a physical prototype. I was also responsible for specifying and ordering the parts needed for the physical construction of the sled. Once the sled was built, I also assisted in testing the prototype on and off the ice. Transforming the design from a set of 3D CAD drawings to a tangible object was my greatest challenge and also my greatest accomplishment. First, it was essential to find specific components that met our needs and were within budget. Then I worked directly with the Drexel machine shop to produce precisely dimensioned drawings for them to make their cuts and welds. After assembling the fabricated pieces on our own, we had a prototype that was ready for testing. Testing was particularly challenging because we had a short duration to test on ice, so we had to be extremely prepared. My next steps include full-time employment at AMA Consulting Engineers as a project engineer focusing on plumbing and fire protection. I would also like to pass my FE exam, continue to refine my design skills, and eventually transition into consumer products or team management.
One of my biggest responsibilities for this project was communicating our ideas between our senior design team and the sled hockey community which we were involved with. I also assisted in the electronics assembly, managed the budget for the project, and designed the verification tests.
One of the biggest challenges of the project was defining the user need and a feasible project scope for the 9-month senior design sequence. We accomplished this by preparing weekly meetings with the senior design team and the sled hockey equipment manager to ensure that our product and the design inputs were meeting the user need. Another challenge was the electronic system design. The electronic system required our group to learn many new skills and perform a lot of research to create a working system that properly met our requirements. Another challenge was the COVID-19 pandemic, which inhibited our use of the Drexel facilities until later in the process. My next career steps include going to work for Merck as an associate specialist in their manufacturing automation department. I will design process improvements and implement automation projects and continue my education as a lifelong learner.
My responsibilities involved a physical sled system design. I developed a CAD model of the sled used for virtual prototype design and was used to create drawings for the machine shop. This also required working in the machine shop to fabricate design pieces for mounting and wire management. I was also tasked with designing and fabricating the tread that was placed on the wheels for on-ice testing. And I used ImageX and Tracker 6 to analyze video to design and test our velocity and acceleration requirements. The challenges of this design were remotely designing and fabricating the sled frame. There was a lot of communication between my team members and the machine shop that made it possible to fabricate our unique sled design into a working prototype. Another challenge was designing and testing a single tread system. This was a high priority item that we needed to work on for the sled to be able to propel on the ice. And through research and collaboration, a tread design was created that was sufficient for testing. And finally, scheduling meetings and fabrication was difficult between team members to exchange materials and ideas in a safe manner, which took a lot of communication and planning. As for what's next in my career, I will be working at Aprecia Pharmaceuticals as a process development engineer, where I've been working my last 2 co-ops and part-time throughout this year. I also plan to pursue either a master's in engineering or an MBA program. I want to continue to develop my process development engineering skill set, which will include beginning a 6 Sigma certification.
For electrical engineering, the electronic system was my responsibility. It needed to function at design specifications while not posing any risks inherent in electrical systems. Based on design load conditions, I calculated required motor force and current requirements. The components were selected based on these calculations, and the circuit was modeled and soldered with signal path and current flow testing done throughout. A small-scale system that deals with both analog variable and digital signals, all while being capable of handling 60 plus amps, is no small order. I ensured that the components, down to the gauge of the wire, would be able to handle what our design required. The power calculations were essential in preventing lost budget on inferior componentry and safety of the system. I am currently in a systems engineering co-op with Lockheed Martin. My main goals from here are to get into an MBA program and start my career as a level 1 engineer. I hope to move into design or R&D, as the research aspect of senior design was particularly exciting for me.